Okay, greetings again. Let's begin anew. It is truly an enormous pleasure to welcome our guest. I do warn you that we're switching languages to English, and I'm very grateful for your indulgence of both myself and our seminar guest today, Ulf Büntgen, someone whose work I have admired, envied, and most of all learned from for a very, very long time. I'll be brief, but formally, to establish the fact, he is Professor of Environmental Systems Analysis in the Department of Geography at the University of Cambridge. He earned his PhD in 2006 in the Department of Geography at the University of Bern in Switzerland, with a thesis on long-term European climate reconstructions from high-elevation tree rings. He is one of the leaders in the field of paleoclimatology, and specifically one of the most important dendrochronologists who has ever worked. His series of papers have had an enormous influence in the field and our understanding of the Holocene, and particularly the late Holocene. Personally, he has papers in 2011 and 2016, the data from which you have seen repeatedly throughout this course. If you've noticed the Büntgen et al. 2011 and the Büntgen et al. 2016 at the bottom of the figures many times throughout the slides in this course. We are very lucky to get to welcome the person who has braved the dangerous mountaintops of Switzerland, of Asia, of all over the world to help us understand the history of the climate. A great scientist and someone that we're very lucky to welcome. So please join me in warmly welcoming Ulf Büntgen.
Merci beaucoup, Kyle. Merci à tous pour être ici. I think it's really better if we switch into English, and I will do my very best that we still have a good exchange of information. So thank you very much, and I will use the next 45 to maybe a little bit more minutes to give you an introduction into tree ring research. So Kyle asked me to really start at the roots, and then we move, so to have basically a common ground that we all know how do we actually reconstruct climate 1,000 or even 2,000 years back in time. Let's see if that should work. Maybe we can switch off the light, that would be good. So it is a tree ring perspective or a retrospective, so we are really looking into the past with an emphasis, and that is maybe a change to the lecture Kyle gave just before me, where he put a lot of weight on solar activity. And when I started 20 years ago, we also looked a lot on the effect of solar activity on the Earth's climate system. And then throughout the, I would say the past 2 decades, we moved more and more towards giving more weight to the influence of large volcanic eruptions. And the interesting thing, and maybe that is connecting our both presentations, if we devalue, decrease the importance of solar activity and increase the importance of volcanic activity, large sulfur-rich volcanic eruptions, we do not change the course of temperature variability. That's a very interesting thing, because solar minima like Oort, Maunder, Wolf-Spörer somehow coincide by whatever reason with large volcanic eruptions. So it's really about the scaling. This is the link to the previous talk. So I will structure my presentation in 3 main parts. The art of dendrochronology, or the beauty of tree rings, and you will see that there is a certain beauty in what we do. The second part, a tree ring-based paleoclimate variability perspective. So I think at the second part here then, I expect us all to be on the same ground. We all know how a tree is growing, and why we can use it as a high-resolution climate proxy. And then in the third part, we basically go really at the forefront of research. I'm reviewing, so I'm looking at state-of-the-art relationships, interconnections between large sulfur-rich volcanic eruptions, changes in temperature, summer temperature, and then its effect. And this here used to be history, so volcanoes, climate, and history. But then I thought, no, it would still affect us, right? This is not something we would only say it's history, so I changed it very recently, probably yesterday, from history to society. Okay, I hope that is a little bit what you expect, and let's go into it. The art or the beauty of tree ring research. And I use this picture because it is just beautiful, right? It is evidence that Iceland was indeed forested. So this is old subfossil relic wood from Iceland. And we very recently dated it to the year 822, so before the first people settled on Iceland. Just to give you an example, this is what we are looking for, old wood. This is the archive. And this is another picture a little bit further to the north and to the west. So this is coastal East Greenland. And I took this picture some years ago, and you are looking out to the North Atlantic. And now we change and turn around and look inland. It's not looking very different. At this moment, you should ask, what is the tree ring researcher, the dendrochronologist, doing in Greenland? Where are the trees? I also couldn't see the trees for many years. We usually say we can't see the forest for the trees, or vice versa. And then we realized, oh, here, or maybe here, it's a little bit green. Maybe there are, and now I changed the word, maybe there are plants. And there are plants. As a geographer, we are used to operate and work with scales to get an idea of what we are looking to. This here is our scale. So it shows you this plant is very small, right? We would all agree this is a small plant. Without the scale, you may have thought this is a big tree. There is a canopy, there are leaves, there is a stem, upright growing, and there is a root system. So from the morphology, this tree is not different than the tree outside. And then you may say, yeah, but you want maybe very old trees, trees that are big and old, large and old. And now you make a mistake, because you are associating size with age. So we are cutting through the stem. We don't need a chainsaw. We can just make it with a knife. And then we see this. We see more than 200 annual growth rings. Okay? So this very small rhododendron from coastal East Greenland, we cannot distinguish it from a big tree that we would know and consider a tree in terms of its morphology, in terms of its age, of wood anatomy, and physiology. So there is basically no way for us to classify in these life forms, trees, shrubs, and herbs. I made this loop here at the beginning because I thought, we all talk about trees, dendrochronology, but we don't really know what is the subject of the field. What are trees? It starts even there, right? We have to ask ourselves, what is the object? And I'm sure after these 5 minutes now, you learned something. right? It changed your perspective. Where is a tree? What is a tree? Yeah, we always thought something big. And now we change the perspective. It's broadening our horizon. That's the important thing. Okay. Now, there is something else we should learn. What we see here, I would now ask the students, how many tree rings do you see? And then they often say, yeah, maybe 1, 2, 3. But that's wrong. What you see is one tree ring. It starts to grow on this side. These are the early wood cells. Right now, when spring starts, maybe next week, if it continues to get warmer, we have light, we will need water, and enough temperature, warms. And then the first cells will grow, the early wood cells. These are big cells with thin cell walls, right? These are the cell walls, and these are the cells. And then throughout the year, into summer and autumn, the cells are getting smaller, and the cell walls are getting thicker. That's clear. So we would call this here the late wood. That's a very simple term. Early, late. It starts early, it ends late. Spring, autumn. This is 1 year. And now, what we see is not only beautiful and art, it always has a function. Nothing is random. In the beginning of the growing season, the tree needs to transport water from the roots in the canopy and actually also back. Therefore, the large cells with the thin cell walls, they are like tubes. Suck the water up, down, up, down. One could say that's enough. But a tree just of early wood would not be very stable, right? It needs somehow a skeleton. And it's genetically induced that always, towards the end of the growing season, it will produce the late wood, which is the skeleton. Okay. So now we know what is a ring. And this ring we can then associate to a calendar year. And I'll show you that later, why it is important. That is absolutely essential because that is our link to the historians. We have information that we associate to a calendar year. If we would not be able to do that, we wouldn't work together. If we are off by 1 year, we have a problem. 1 year off is equally bad as 100 years off. We have to be precise. I come to that later. Now, another example of perspective. This here is a piece of wood. And normally, if this is our tree, we cut it, and we look on it, we see the tree rings, right? That is the most common thing. If you go in the forest, if you see something that is a cross section, that's this here. Here are our rings. Here's a one ring. This is a cross section. But we can also cut the same piece of wood, make a radial section. So if a radial section, and then if I would ask my kids, they are very young, cut the piece of the cake, they just take the knife and cut it like this, so which is then the tangential section. They mess it up. The point I want to make here is it's the same piece of wood, and just depending on how we look at it, we see something different. That looks different than this and this, but it's the same thing. Different perspectives all together provide a more comprehensive picture. So it really shows us how is actually this three-dimensional object stem working. And if we ought to understand climate later from tree rings, we should better know how a tree is growing and functioning. Now we are all getting slowly on the same level. You are becoming dendrochronologists, tree ring researchers. And the next question would be, how many rings do you see now? And then you would say, 1, 2, 3. And some of you may say, I see 4 rings. 1, 2, 3, 4. So this here is a very, very narrow ring, right? Just 1 early wood cell and 1 late wood cell. A super, super narrow ring. Huh? So I'm showing you that we are really operating at the cell level. And these rings, these are then informations for us, right? So the tree is sensitive. A tree ring can be wide, it can be even wider, it can be very narrow. Now, when you are looking at this slide, I'm very sure that most of you already see a pattern without me saying anything. You all likely focus on these lines, right? You did that. You are not looking here too much. Your eyes are not spending too much time in this part. You're automatically focused on these lines that go across. So these are pieces of 3 different oak trees. And they were most likely, you would say, they were probably growing at the same time in the same region. Because something external, abiotic, affected their growth. And this is particularly the case in so-called pointer years, like here and here and here. What you see here is a visual example of what the tree ring researchers call crossdating. This ability to match the growth patterns from different trees, individual trees, against each other. Now we come back to the annual resolution. This is a year, this is a year, this is a year. The number of small rings here in between must be the same on this disk, then on this, and on this. If we would count it, it must be the same. So it helps us to really precisely cross-date. And with this, we are able, for instance, to contribute to archaeology. We provide dating, so then in this case, dendrochronology is a simple dating tool. This is a well construction, quite nicely crafted. It's good shape. This is oak. I don't ask you, I ask him, how old is that? Just roughly, it doesn't matter. Just 2,000 years. So that would mean Roman times, right? Roughly. I would also say, maybe this is medieval times. Look how well they crafted it. So 1,000 years. I give you the answer. It is 5,200 years BC. 7,200 years. Early Neolithic revolution, the so-called lineare Bandkeramik. So this is one of the oldest construction woods we have, right? This has been crafted 2,000 years before the invention of iron. Just keep that in mind. It's a beautiful piece. You were slightly off, Kyle. So just as an example, or here, what is this? I don't ask you anymore. This is driftwood. In Greenland, there are no trees growing on Greenland unless the small ones. So this is an example of wood that is coming from the boreal forest, likely from one of the big river systems in Siberia, the Lena, the Ob, the Yenisei, the Indigirka. And if we take a sample, we can date that. We can say when was the tree growing and also where, in which catchment. So it's a provenancing, the tracing of the origin of Arctic driftwood. This is a beautiful example. We use a terrestrial archive, trees from a forest, to actually reconstruct changes in ocean currents and sea ice extent. So we are using a terrestrial archive to reconstruct marine processes. But I'm not talking about that today. This here that is the oldest one we have. This is, and you see, this is a clay package, so that was an excavation. Here are the roots and here's even bark on. So the tree was really growing there. That is in situ, right? And it's a pine, Pinus sylvestris, and it's one of the first forests, I would say, because we excavated 280 of them in the same construction site in Zurich in Switzerland. So these were likely the first trees that were growing again after the last ice age north of the European Alps. This material is 13,400 years old. If you take it out, if you cut it with a chainsaw, you would ask, how old is it? You would say, oh, maybe 5-10 years. There is no way for us to say how old it is unless it is dated, right? Because once the wood is preserved, like here in anaerobic conditions, like the well construction that was excavated, it can stay forever. It's perfectly preserved. Okay, and now I show you what we don't do. This is an example of tropical wood, right? This is just in a container, tropical wood. All our work is outside the tropics. On the northern hemisphere or on the southern hemisphere, mostly on the northern hemisphere, but it is outside of the tropics, so we call it extratropics, for one reason, which you obviously know, but I will remind you. We need an annual cycle in the climate system. We need winter, spring, summer, autumn, winter. Otherwise, we don't have this formation of a clear ring that we can associate to a calendar year, right? So the tropical wood is beautiful, has lots of arguments to analyze it, but not for the dendrochronologist. So we need this annual cycle in the climate system in order to have a very precise cross-dating. Okay. And now we move over. It's another example. So from the Lena Delta in Siberia, we were traveling for weeks with mammoth hunters. They are interested in finding old tusks. And we just look for wood coming out here of a permafrost erosion slope in the world's largest delta. That's the Lena Delta. Okay, I'm now giving you an example of how do we actually reconstruct climate, right? How do we do that? And the closest example to France, but it is not France, are the Pyrenees. So we have a site here. This is here's the French border is basically here. So we have Andorra, we have the French part of the Pyrenees, and then we are just, I would say, 20 kilometers south of the French border in the Parc National de Aigostortes. It's pretty much in the center of the Pyrenees. And it's beautiful. So what you see here in the back, this is already in France. So that was the closest I could give you. And then we have living trees, dead material preserved, and we collect a lot. So don't think that 1 or 2 trees are enough for us, right? So each of these horizontal green lines represents 1 tree. So we have, almost 600 trees just from this region. And the time scale this is 2000, this is basically present. So we are here at the outermost ring is 2020. So it's a very new data set. And the oldest trees, or the oldest rings we have are 1,000 years back in time. So we are now talking about the last 1,000 years with Kyle's lecture, basically then here from what he identified as the Little Ice Age or the Little Ice Age type events. I liked that a lot, that you were referring to these different parts, around from the 13th century basically to the early 19th century. This is the period we are covering. And now we want to see what is the model, what is the climate signal. In this case, we always talk about climate change or climate, but we either should talk about temperature or hydroclimate, precipitation more, right? And with climate, it's already very, very vague. It could be everything. Huh? So in this case, we talk about summer temperatures. And you know that the trees cannot tell us anything about winter. You know that now. It is really the growing season, the warm season. And in this case, it's a mean from May to September. May, June, July, August, September. Temperatures. The trees are the green one. So now we have the period of the instrumental measurements. So we look 100 years back in time, from today to the early 20th century. And the trees go up, down, up, down, up, down. And then the target data, these are instrumental measurements for the Western Mediterranean region. Yeah, they are spot on. They show basically the same. They have very, very high correlations. And now another homage to the French Meteorological Society. So we take data from the Pic du Midi station. This is an outstanding station worldwide. It is the only summit station outside of the European Alps that has a long record. And we can see the Pic du Midi, basically temperatures behave in the same way. So this is our temp. So there we built the model. This is the overlap. We always need the overlap between measured climate parameters, temperature, and the proxy, the wood, to build our model. Here we look in time. Is that stable? Do they capture the same year-to-year changes, longer-term changes, trends? And here we look at the spatial signal. So we are correlating the tree ring data against gridded climate data. This is very simple, and it shows us, yes, the data come from here. The model doesn't know that. And everywhere where it's white, we don't explain variability. And everywhere where it's dark red, that's a region for where our climate or temperature reconstruction is representative. And this is the same, you would say, yes it is, but here we basically correlate the Pic du Midi station measurements against the gridded data. So it's a confirmation that the pattern we get from the tree rings is robust and really reflects meteorology, climatology. And I call that now, this is a temperature reconstruction for the Western Mediterranean region. You see that perfectly, right? And we know that we have a dipole, that if it's warm, or not, no, it's not that clear of a dipole, but it is a difference if you are in the Western Mediterranean or in the Eastern Mediterranean. They don't have anything to do with each other climatologically, and that comes out here. And we don't have correlations for lots of Northern Africa because we don't have climate data. Okay. And this is how the result looks. This is a way of how we show now our reconstructions. People are getting more and more interested in this kind of visualization. You know that it's used in the IPCC to inform policymakers, or policymakers are using it to inform the wider public. These color stripes, yeah, it is very warm here. This is a recent anthropogenic warming. But if you go back in time, you see periods that were also warm and cold. And the more traditional way, how we show it, is like this. So this is our, now it's very new. It's actually published last year, or actually early this year. It's a almost 1,000 year long, annually resolved and absolutely dated temperature, summer temperature reconstruction for the Western Mediterranean region. So we know how temperatures were varying, up, down, up, down. This is the most recent warming, and then you have the context here. And we are interested in what is causing these changes. And I do that very quickly only. We looked and you could see, okay, I make one example here. If we would look in the data and say, what was the coldest summer in the Western Mediterranean of the last 900 years? We would look in the numbers, and it is 1258. You should remember 1258 from Kyle's lecture because he talked about Samalas in 1257. The coldest year of the last 1,000 years in the Western Mediterranean was the summer of 1258 following the Samalas eruption in Indonesia. We're coming back to that. We're coming back. And then the last thing for this, for the Western Mediterranean, that is where we could connect or should connect and work together between climatologists and historians, is then to link and look I would not go that far and say, can we explain changes, societal changes, transformations? But we are at the stage, because data on both sides, natural and social sciences, are getting better. We can at least and should compare them. Very neutral. We certainly should not become deterministic. But we are in the position now to compare these data. So another thing, so you know we have these rings and we usually look between the rings. How is one ring compared to the other one? Wider, narrower, more or less wood density. But there is another thing where we look basically at the intra-annual level. We look into a single tree ring, so we use wood anatomy. Now we add another 1,000 years, so we have the 2,000 years here. These are temperature reconstructions, again, from tree rings, right, for the northern hemisphere. So now we are zooming out from the Pyrenees. We have northern hemisphere extratropics, summer temperatures for the last 2,000 years. What was the coldest period for the last 2,000 years? That was the so-called late antique little ice age, 536. We come to that later also with the volcanic eruption. That's this period here, and it's coinciding with volcanic forcing. If we zoom in, we see, oh, 536, it really goes down. But then it continues, 540, 541, 543, 545. There is this trend that is basically this part here. It's getting cooler, rapidly cooler. And we now want to look into these years in particular and keep our perspective large scale. This is a global network. That is very important that I now use the word global and not northern hemisphere. Because for the first time, we included sites in South America, Argentina and Chile, Tasmania and New Zealand. These are the only sites on the southern hemisphere where we could expect a temperature signal in trees, right? I mean, there is just this huge and massive difference in landmass between both hemispheres. And everywhere here we have our sites on the northern hemisphere. The European Alps, Scandinavia, 3 sites in northern Siberia, the Altai, Mongolia, the Tibetan Plateau, Quebec, and the western US, Alaska. So that's where the trees come from that could potentially show a temperature signal. And we look into these rings and we focus on the onset of the late antique little ice age, 530s. This is a blue ring. So you see that it's blue rather than red because we use a double staining, astra blue and safranine. Cells that are not lignified, the cell walls, will turn blue. So there would be, we say that is due to a lack of warmth. So it's too cold for the plant to lignify its cell walls. Or a frost ring. So if the tree is already growing and it gets rapidly cold in the growing season in spring, so you know that late frosts, you also know that if you are a farmer, a frost that can come in can damage the plant. Yeah, why? Because it's already sucking up water in the stem, and that is the same if you forget your bottle of champagne in the freezer overnight, you take it out the next morning, the bottle is not good. It's broken because the water or the champagne expanded, and then when it's thawing, you have the collapse of not the bottle but the cell walls, right? So that's the same process. And then we have these light rings, basically a lack of late wood. So these are all 3 anatomical features that is now important. We look into a single ring, intra-annual, and have anatomical insight. So we really work, I love this study because we basically use information from the cell level to explain something at the global scale. And we did hundreds and hundreds of these slides. That is very complicated to do that. I can't do that, the technicians do that. And then we are now 530 to 550. So just 20 years around the so-called beginning of the late antique little ice age. And then we see, wow, we have really a cluster. Most of these anatomical features that are referring to very cold, short but cold temperatures, or short periods of very cold temperatures in the growing season, 536, 541, and then again 548. So there must have been most likely a cluster of 2 to 3 larger eruptions that then basically had this feedback effect on the Earth's climate system that triggered us into the late antique Little Ice Age. That is also actually the biggest difference between the late antique Little Ice Age and the Little Ice Age that you were talking about, is that here we know exactly when it started because we know what happened, volcanic forcing. And for the if you ask 20 scientists when did the Little Ice Age start, you get 20 different answers, as you pointed to, because we don't have an understanding of what triggered it. And Samalas is not the trigger. Now, another example, so that you are really becoming advanced tree ring researchers. We are not only measuring how wide the rings are, we also extract cellulose to measure stable isotopes, carbon and oxygen. We only do that if the ring width, wide, narrow, doesn't work, right? So then we have to invest a lot, use very complicated and very expensive mass spectrometers, take the cellulose into it so that we extract from the annual ring, so we had annual resolution, and then we build up these records. This is the first 2,000-year-long continuous tree ring stable isotope record, living trees, oaks, historical construction timber, subfossil wood coming out here out of a river bed. This could also be the Moselle or the Marne or so. These rivers have a lot of, in their gravels, a lot of subfossil wood, and then archaeological material. 2,000 years, you know now these figures. We have lots of trees. In this case, they don't come from France or Germany. They come from the Czech Republic mainly, but it would be the same if we go to Lorraine or so. And then we have these two isotopes, stable carbon and oxygen. For 2,000 years, they more or less show the same. We combine them, so we use a combined approach, carbon and oxygen. Details are not important now. But what we see whenever we combine the two isotopes, which is here in green, we have higher correlations to climate, right? So you could say use carbon or use oxygen or somehow try to combine it and get even a stronger climate proxy. Actual and reconstructed, you know that exactly from the Pyrenees example. We have our proxy and our target, but now we don't have temperature. We have hydroclimate. So these isotopes help us to reconstruct precipitation, but that alone is not all. So we call that soil moisture availability. How much water is accessible to the tree for the summer? So was the summer drier or wetter? Representing Central Europe in this case, and that is the reconstruction. 2,000 years, or actually almost 2,100 years, and we were able, and that is an importance of this study, to place the most recent droughts. And you remember that, 2018, 2019, lots of forest dying also in France, in Germany, in Switzerland. It's just getting very, very dry during the summers. And we were able to place these most recent drought extremes and heat waves into a context of the past 2,000 years. And the very, very important thing, I want to emphasize it here, is this long-term trend. So this is a very long-term trend, right, that we are capturing with the tree ring stable isotopes. Imagine now, just imagine, we would not have this trend in. We would take the orange line down, that it is stable. And then this period, this period, this period, and this period would be lower, right? So we just take the trend out. The whole story would change, because we would not say anymore that the most recent droughts are that they are unprecedented of the last 2,000 years. We would say, yes, they are in the same range like previous ones. So preserving this very long-term trend seems to be essential. And that is something tree ring stable isotopes can do, but the traditional parameters, ring widths, most likely not. They seem to be limited there. Okay, this is important because these tree ring reconstructions that you now really have a good understanding, what do we need? Where is the wood coming from if we want to have 2,000 years? What can they do? They say something about summer, not about winter, and so on. They are the only tools that help us to contextualize recent warming. You all heard in the news 2023 was the warmest year on record. That was now in the news everywhere, right? Yeah, this is 2023. Here we have the instrumental record, so we go back basically to the mid of the 20th century. It's getting warmer and warmer and warmer and warmer and warmer. And you have these spikes, and they always coincide with El Niño years. So we know 2023 is obviously a result of greenhouse gases, anthropogenic warming. Superimposed on this long-term trend, we have the effect of a yet unfolding El Niño event. So it is most likely that the 2024, this year, will be even warmer, right? Okay, but now, if we say, oh, the last year was the warmest of the last 100 or even 150 years, that is a strong statement. But if we are able to say 2023 was the warmest year of the last 2,000 years, this is even a much stronger statement, right? And in order to make such statements, you need the proxy data. The proxy data are tree rings, nothing else at this precision and this time scale. So I hope that you have an idea now. I have a couple of more minutes. What can tree rings do and what can't they do? And why are they helpful? And now we go in the third part of the lecture. That is a global overview of volcanoes, climate, and history. And I speed up a little bit. I have to, unfortunately. So there is a hierarchy in this part of the lecture. I go back. Volcanoes, climate, and society. The first information we need is to have knowledge about large volcanic eruptions. This information does not come from the tree rings. That comes from the ice cores. Okay? So we have ice cores that are reliable in Greenland for the northern hemisphere and in Antarctica for the southern hemisphere. So 2 points in the world, not like our tree rings everywhere. Ice cores, Greenland and Antarctica, and there we have depositions of sulfur. So the black triangles, so we are now looking at the last 2,000 years again, right? It's a common era. The black triangles refer to volcanic induced sulfur depositions in ice cores. You showed that a little bit. If I would ask you now, which triangle is at the highest position? Yeah, this one, right? Quite clear. Which year is that? Oh, 1257. That is our Samalas case, right? Okay, that all fits together. We jump. So this is the ice core evidence for volcanic eruptions. Now, for the climate, these are the tree ring records, and you now know where the wood comes from and how that works. So we have ice cores for indicators of volcanic eruption, tree rings for indicators of summer temperature. And what I then did is a literature review. What do we actually know about this interface between volcanoes, climate, and history? There are many, many studies that looked at the effect of volcanoes on climate. And there are many studies that looked at the effect of climate and society. But there are not many studies that looked at the effect of all three: volcanoes on climate, climate on history or society. And that is what I looked into. And that is the first summary figure. So we have our last 2,000 years. We have our volcanic eruptions, and I now used Pinatubo 1991 as a threshold. So we have much less black triangles because the small ones, the background noise, I deleted. And then we looked into those, in all of them, for the climate response, right? So just as an example, the first large sulfur-rich eruption we know from the ice cores would be the year 807. The next one, 169. The next one, 266. All three of them don't leave a cooling. So we are not interested in them. The first one that matters for us is the year 304. Ice cores would say, wow, strong, large, sulfur-rich volcanic eruption. And the tree rings would say, yes, and in the same year or the year after, a cooling. So we go through, and you see the strongest example is 536. That's massive, right? That is the strongest cooling after a sulfur deposition. Now an interesting case I want to make, because you said 1458. It is actually 1453. It is 1453, the large sulfur-rich volcanic eruption and a strong cooling. And down in this part, this is where scholars looked at. So people, like Kyle, like me, like many of you and others, looked into the link between a potential yet unknown volcanic eruption, cooling, and society in 536. But we can now identify, no one looked at this for 1453, 1345, 1 year before the outbreak of the second plague pandemic, the Black Death, the same, but no literature, no studies on that, right? So this is an overview I'm currently working on. It's a fascinating thing. Then if we would zoom in, we can really see how long are these cold spells after volcanic eruptions. And so they are aligned here by the year of the eruption, all of these cases, and then we see, it's warm, 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 and then the rapid cooling, and it actually takes more than 20 years to recover. This is longer than I would initially thought. Then if we have such a database now for the first time, we can look, and that is an interesting one, in the relationship between what the ice cores tell us about the forcing and the real response. So according to a very linear relationship, we would think Samalas, that had the strongest sulfur injection or deposition in the ice cores, would lead to the strongest cooling. So this relationship we don't have, right? There is no clear relationship between the amount that we find in the ice and the real cooling, which is a problem because most of the climate models would use it like this, right? They would use the injection intensity to say it was very cold or a little bit cold. And then we also looked into the relationship, and I think that is something you are interested also in, Kyle. Does it matter if a volcanic eruption occurs in a cooler or generally warmer period, right? During medieval times or during the Little Ice Age? And again, we find no clear relationship. I skip this here. I also skip this and go to the last slide. This is now the overview of this review, right? So these are the eruptions that people looked at. There are also many unknown eruptions. And you see there is still a lot of room for doing studies because most of the examples, volcanoes, climate, and history, are in Europe, some in China, Europe, China, North America, a little bit Mesoamerica. No examples for the Southern Hemisphere. No examples for large parts of inner Eurasia. And I think that's it. That was a lot. It's not fully finished now. And I think like I'm tired, you must be tired. And again, I apologize that I'm not doing that in French, but trust me, this is a better version. It was a better version. I finish with this one here because that brings us back to France. That is the plague, or the Great Plague of Marseille, 1720. And I'm showing it because you should also see we are not stopping, we're continuing. We just got an ERC grant from Brussels of 10 million euros to work exactly on things that Kyle and many of you are likely interested in, is to reconstruct and understand the environmental, biological, and societal drivers of plague outbreaks, right? So it's exactly this interface, climate, the ecology we haven't talked today a lot about on plague. And I hope you now realize that dendrochronologists, tree ring researchers, do a little bit more than just counting ring by ring by ring. So there we can do, I think what we can do, we can contribute an archive and a tool to other disciplines. So we are basically just supporting others, ecologists, biologists, historians, archaeologists, with temporal information. And that's it. Merci beaucoup pour votre attention.